en GitHub? Súper. ¿Pueden buscarme? ¿Sí?
Hay alguien de Brasil, así que podría ser en inglés.
Ah, yeah,
Sí.
sure. I didn't know about it. Okay, so let's do it in English then. So if you guys use GitHub, can you just go to my account? And then you need to search for this neural network and interpretability lecture. There, yeah, sorry, just there, like, there it is, like, neural network interpretability lecture. Yeah, or yeah, that's a good point. Okay, thanks. That's a good point. Sometimes I forget we have the Slack channel. So once you're there, is everyone there? Yeah?
I sent it on the slide.
Yeah, sorry, again. If you open it, you're gonna find in the README file the main notebooks that we're gonna use for this session. So the first one is gonna be like an introduction. The second one is going to be about supervised learning. Then we're gonna talk about neural networks specifically. And then we're gonna see an example of the cosmic microwave background. And then you're gonna have to do something for me this afternoon. So let's get started. And also, if you have any questions in English or in Spanish, I don't speak Portuguese, I'm sorry, but but you can just let me know. You can just interrupt me, please. Feel free to interrupt me whenever you want. So let's start. My name is Indira Ocampo. I am a PhD student at the IFT in Madrid. Maybe some of you know about it. And I'm in the last year, so yeah, a bit busy. So this is the outline, as I was telling you before. There is like an arrow, right? Oh, I cannot believe it. Somebody make a mistake, right? So first, let's okay. Let's talk about machine learning. In machine learning, we have mainly three approaches: unsupervised learning, supervised learning, and reinforcement learning. Neural networks are part of the supervised learning approach. And supervised learning usually is when you have data that you cannot, let's say, give to your algorithm a particular label. For example, you have this data spread. We know, as we can see, that there are some data that are blue, there are some data that are red, and some data that are green. But let's say that you don't want to give this information to your particular algorithm. So you just say, we have this data, you classify as you can. So let's say it's self-taught, it automatically is able to discriminate between these colors without us specifically saying, hey, these are the colors, just classify them. We're not gonna talk about this much because we are going to focus on neural networks, as I told you before. The supervised learning approach, in this one, we need to tell the algorithm which are the labels. So in this case, for example, I would train an algorithm saying, I have circles and crosses, and can you please differentiate with the data? So this is why it's called supervised, because you supervise the process. And then we have reinforcement learning, which is more about like gaming, you know, like you get some, how do you say, some feedback when you have when you perform good. Like gamers usually, people who develop games use reinforcement learning because whenever you do something right, you get like a feedback, you get some positive reward. So we're also not going to talk about reinforcement learning because it's more for like gaming, let's say. In science, mostly in cosmology, we have unsupervised and supervised learning. Okay, I'm gonna have to move this. Maybe down there. Okay, perfect. Okay, again, but it's the part of reinforcement learning, so it's okay, it's covered. So as you can see, there is a very wide landscape of machine learning algorithms. We have, from the supervised point of view, we can do classification or regression. And when we talk about classification, we can do image classification. For example, you can train an algorithm to do classification of galaxies, of images of galaxies or other like celestial bodies and so on. And for regression, you can usually predict some quantity that it's continuous, like the classification is either class 1 or 0, but the regression is some quantity that is a continuous. For example, it could be like a luminosity or some other quantity. And in the unsupervised learning, like the algorithm learns to cluster, let's say, the data by the features without us supervising it explicitly. And then we have dimensionality reduction, but we're also not going to talk about much the unsupervised part. So we're going to actually be very specific on classification, because it's, let's say, the most straightforward exercise and the one that is more visual to learn machine learning, how to apply it. So let's go. I need to do something with this. Maybe there. Yeah, I can hide it. Okay, perfect. There it is. Good. So I'm going to start with a very, very simple physics 1 case, which is a linear regression, right? We know which are like the inputs, the outputs. We have the like y equals θ1, which is going to be the intercept, and θ2, which is going to be the slope. And then we have some scattered data. We do the regression. We fit this parameter, and we can know θ1 and θ2, right? And how can we know if our fit is a good fit or not so good fit? We compute this mean squared error. And so we compute the differences of each one of these points to the actual predicted. And this is going to give us an insight of whether our fit is good or not. This is important in machine learning. Maybe you're saying, why are you talking about linear regression? This is physics 1. But okay, let me open my own repository, which is this one. So you are going to find this notebook in the, here in the introduction. You can just open in Colab. You can clone it or download it if you want. I would say that it would be better for you to run directly in Colab because you don't have to install anything. So you can just run everything as we are going step by step. I'm going to do it locally because I like to code locally or in the cluster, but okay, whatever. So you should be able to see the first notebook. Is everybody with me? Yes? Can somebody raise their hand if they didn't manage to? No, everybody is there? Okay, cool. So you should be seeing this, right? 0, introduction to machine learning. Good. So what we are going to do first is that we're going to simulate some data set. Okay, it's going to be the global. So I'm first importing all the packages. I imagine that everybody here codes in Python, right? Okay, cool. Yeah, because sometimes it's like, no, I actually code in Fortran, and I'm like, sorry, that's too advanced for me. Okay, so what we are going to do is that we are going to simulate some data based on, actually I'm projecting. Cool. So we are going to simulate some data based on a linear regression, right? We're just having some scatter. We know our x, our y, that is our observable. And now we know from our model that, okay, y is going to be f of x, ax plus b. We have the slope and the intercept. You run the next cell. And here we're going to define the model. Yeah, here. So we just define the function, ax plus b. And here, this is going to be my loss, right? The one that I showed you before. So we run that, and then we compute, can you run that one? Yeah, okay. It's our loss, it's 0.26, right? So it means that Our fit is not so bad, I think. Yeah, because we have the true values. Okay, sorry. I think I'm maybe skipping some steps in between. I just said we're going to simulate the data. Okay, so first we're going to define a true A, a true B for simulating our data. We're going to give some noise, which is our sigma. And then we are going to simulate this data based on the true, right? We're going to plot the scatter. And now what we want is to define the model for doing the fit over our simulated data. Sorry for skipping that step. So now we have computed the loss. And what we want actually is, can you run the next? So here we have, let's say, all the values of A that we are trying to explore and the values of B, which is the intercept, right? And our two parameters are here. So it means that this is the loss landscape, meaning that it's getting lower whenever we get closer to the true parameters. So I know that maybe you have already seen this before, but it's a good review to get intuition on exactly what happens with the loss when we train a neural network model or a machine learning model in general. So the idea is that we're going to have a loss that we need to minimize. We need to minimize the loss so that we can get very close to the true parameters. Well, true parameters. Now I have true parameters because I am simulating the data, but in real life, we don't have these true parameters, right? We just need to get as close as we want to what we believe is true. Okay, but how do we do this linear regression with the... So I really love this kit. It's called scikit-learn, and they have many machine learning algorithms, as many as you can imagine. So you just need to import it. In our case, we're just importing linear regression. And then we're having our, let's say, the parameters that we want to estimate from our simulated data. So we're going to have A hat and B hat, as you can see here. So we first import our linear regression. We define the model. We make a fit with X that is going to be like, where is the X? Sorry. Yeah. With X that we're just going to have some input values, let's say. We're just going to have some input values. We're just creating some vector. So we go again. And the idea is that we're going to find new values for A and B, which are going to be our fit values. So when we run this, you can see that the true values that we used for simulating the data were these 1.8 and minus 0.4. But then the updated values, like not updated, but the fit values that we're trying to estimate were kind of close, right? Because again, if we go back, this is the parameter space, and more or less, maybe because we introduced some scatter, we introduced some noise, then it is a bit deviated, right, from the true values. Okay, and here, from the fitted model, we see that the loss is going to be 0.26, so not so bad. Could be worse. And then we see our linear. Let's run this 1, 2. And then we see just our fit line over there. Okay, this is an extra. I'm not going to cover it right now, but this is just a review. Now, let's go back to the slides. And let's talk about logistic regression. Has somebody here heard about logistic regression before? No one? One? Maybe? Okay.
Yeah, I have a question.
Yeah, tell me.
On linear regression, your mean squared error is a loss function that has like a global minimum, right?
Yeah.
So it's possible in principle to find the optimal parameters.
Yeah.
But in general, that's not the case, right?
I think in this case, because we are simulating the data, so we are introducing scatter, and yeah, it is a global minimum, as you say. Yeah.
But always is a global minimum?
Sorry?
Always is a global minimum?
The idea is that you find the global minimum. So this was a linear regression example, but in neural networks, you can have the case that you have, for example, here your laws, right? And here you can have like some, I don't know, step, whatever, epoch. And then you have a function that it could be like this, you know? So you could be trapped here. If you need to explore the parameter space, and what happens if you get trapped here, then your feed values are not going to be close to the true values in this case, right? So you need to explore all the parameter space so that you can find the global minimum, so that you can really, yeah, you need to explore all the parameter space. I'm going to talk about this a little bit later, because at least when you work with neural networks, there are some, how do you say, optimizers that you can fine tune so that you can not get trapped here, but you can go all the way down, you know. That makes sense.
To ensure the global minimum.
Yes, to ensure the global minimum. It happens many times, that you are like, oh yeah, I trained, and then you realize that you are trapped somewhere in the global, not in the global minimum, but somewhere locally, and then you need to fine tune a little bit the parameters so that you can go to the global
In
minimum.
that case, the parameter space, it's important to identify the global minimum.
Like to, yeah. Yeah. So let's go to the logistic regression part. This is a little bit, let's say it's a step beyond the linear regression, because the linear regression is just a line. But when we talk about logistic regression, what I want you to get an insight of what is an activation function. So the logistic regression function has this shape, which is like 1 over 1 plus e to the minus z, and it has this behavior. Usually you can have, like, if we talk about the linear model, right, like some inputs, then you have like some weights, like these weights are, if you remember our linear regression model, they are similar to this slope, right? And then we have a bias parameter that if we also map to the previous case, it's going to be your intercept. So it's kind of based in linear algebra in a sense, let's say, but with the nuance that you're going to have now an activation function in every neuron. Like, so let's say that this is just going to be, you have your input, you have one neuron, and you have an output. Say, yeah, like, I'm going to explain later, like, what are the parts of neural networks, but just right now, imagine that we only have one neuron, one layer, one input, and one output. And in this case, we're going to have, again, the inputs are going to be the X, and the outputs are going to be the Z, but these outputs need to be passed through this sigmoid function, which is going to be the activation. So once we do this, why is important? Sorry, why it's important? Because you can actually amplify, you see, if you have this point here, and you do this transformation from, let's say, just the simple line to a linear, to a logistic regression, then you can actually, let's say, this point is going to be in 1, and this second point is going to be in 0. So this is why I was saying that it's important in classification, because it kind of calculates a probability, you know. So it calculates a probability, and then you can put a threshold for saying, okay, from this point up, I'm going to get all these data that are going to be classified as whatever, spiral galaxy. And from this point down, all the data are going to be classified as, I don't know, elliptical galaxy. So that is more or less the idea. And that is why we need activation functions. They are non-linear. Otherwise, if you have like many layers with a lot of linear regressions, we're just summing up, let's say, summing up and multiplying. But then you're not adding like any non-linearity, and the non-linearity is good for learning, let's say, the curves in the parameter space of your data. I'm not a mathematician, and I didn't do these algorithms, but they work. So let's go to the second. We go, we go to the second notebook, which is supervised learning. So you should be seeing this one. And then again, I'm going to open it locally for me. Perfect. So again, here we're just gonna import the packages. I already told you what is supervised learning, but I just wrote some notes in case you want to study by yourselves, I don't know. And then, okay, let's get this example. Say that we have this data. So it's kind of three-dimensional because you have one parameter, the second parameter. For example, it could be any luminosity against, I don't know, lux. I don't know, just two parameters. And then you have the blue dots and the red dots. So the idea is that you need to be able to discriminate between them. So you need to draw kind of like a frontier of discrimination. So we're just going to play with this, as I told you, with the logistic regression model. In this case, we're just simulating the data, so you don't need to like go through all the simulation part. It's just like make moons, which you can import actually from the scikit-learn that I was telling you before. So we import it. And then, okay, now let's start to actually train a model. For the training, you need to have all your data set and you need to split it in training and validation. Actually, you need three data sets, like training, validation, and test. But because we are having a pedagogical, let's say, approach, we're just going to work with the train and with the validation. So the X is going to be the parameters X. It's a vector, right? It's X1 and X2. And the Y that you can see here, validation and train and validation, is going to be the label. So meaning blue and red. But how do you encode these labels? Because you cannot give your algorithm blue and red, right? How do you encode them? Just 0 and 1, exactly. So you can assign it. You can just say, okay, blue is going to be 0, red is going to be 1. And here, what is interesting is that you can actually say what is the size of your test set, what is the size of the test set that you want. And then it's important, of course, to don't forget the random state because you need to ensure reproducibility, right? If you don't fix this, then every time you're going to get different training sets with different values and different validation sets. So if someone else just downloads your code, they are not going to be able to get the exact results that you're getting. So just be sure about this. And the stratify is just an option. Yeah. It doesn't matter too much for now. So let's run this part. And now we have, usually like the good practice is that the training size should be 70% of the whole total data set. And the validation is going to be 30. Like usually when you do research, it's actually, if you have the 100%, usually is like, this one is going to be 70% of training and 30 of test. But then this one, you have to split it again. And this is going to be 20% of validation. And yeah, the 80 remaining is going to be the actual final training. Sorry if you cannot read it. Is it too small? Yeah, maybe. But you got the point. Now we're just working like this. Okay? 70 and 30. That's it. Okay. So now let's import our model. As you could see before, scikit-learn has already the logistic regression. So you just need to import it. And now we define the model. So we define logistic regression. And now we're going to fit our model with our training set, the parameters X and the labels. Is everybody with me? Yes, good. So once we train the model, now what we want is to predict, right? Okay, maybe here I made a mistake and it shouldn't be train, it should be val. Sorry. I'm sorry. Oh, what? Sorry. Yeah. No, yeah. Sorry. It was okay. It was okay. Sorry. So, okay, again, this is pedagogical, but usually when you train a model, what you are doing is you are computing the slope, the intercept, right? You are updating this, what I told you, the weights and the biases, which in the end are just going to be the slope. In the end, they are just going to be, oh, wait. So we have this. In the end, we're just going to compute this slope, sorry, the intercept and the slope, like the θ1 and the θ2. But with the small detail that we're gonna have, the activation function. Tell me.
Because we are working with logistic regression.
Yes.
In which we use a signal function to introduce nonlinearities to our
Yes.
But here it is a linear classifier, so that will be a linear regression. So why is
No, yeah. This is actually a question that I also have. But the idea is that what is linear, we say linear classifier, because the logistic regression is going to be able only to draw a frontier that is going to be linear. You need more neurons to get the curves, let's say. We need more activation functions. Like it's linear in the sense that the frontier is linear, not that the nonlinearity of the, the nonlinearity of the function is one thing, and the frontier that you're drawing in the classifier is what gives the name to the linear classifier as like one neuron with one logistic regression. So it's just the, you can go again. It's just the frontier because it's linear. You are not going to be able to get all these curves, let's say, all these non-linearities in the parameter space. We're just going to be able to learn these, unfortunately. You need more neurons. So it's called linear just because of the frontier, because the frontier is just a line.
but in this case only a linear regression logistic regression, because a linear regression would be also able to produce a line, right? So why are we using a logistic one instead of a linear?
Because the linear regression, sorry to interrupt, because in the previous case, we were just working with one-dimensional case, and here we're working with a two-dimensional case. So the linear regression, you just have one vector and the labels, and in this case, you're gonna have, it's a 2D case. I don't know if that makes sense. I can make the exercise actually to like for the afternoon or for tomorrow, if you want, to make it clear like how this would be implemented only with the linear regression. But in principle, if you're working with high dimensional data, the logistic regression, I know it's called linear classifier and it's a bit misleading. You are right. Okay. So again, the idea is that when you fit the model, you're gonna fit it with the training set and with the labels. And then what we're gonna do is that we're going to predict the probabilities. First, we're gonna have probabilities because as I told you before, where is it? As I told you before, the sigmoid function is going to give you some values between 0 and 1, right? So if I get the data that it's going to have the probability of belonging to class 1, that is going to be 0.70 something, So we want to output all these probabilities from our data. Okay, so this is what the prep does. And okay, and here we're doing with the same training set, just because this is pedagogical, but here we're doing with the validation set. So meaning this data that says xval is the data that our model has never seen. The xtrain, we already used it to train, but it's just to check. And then the second one, it has never seen. So we want to see what is actually the accuracy, which is just like we are trying to compare which is the amount of data, given that it has a label that is blue or red, it's been correctly classified. So you compare these two and then you compute the accuracy, which is like the percentage of correct predictions, let's say. So, and now finally, okay. And of course, in the training is going to be higher than in the validation because the validation is the data that it has never seen. And of course, it has some mispredictions because it's not able to capture the whole curves and nonlinearities in the parameter space, as I told you before. But the idea now is to plot this frontier, like what we were discussing a little bit before. And this is the frontier. So of course, you can see that there are some data in this region that are red, but they are being misclassified as blue, and so on, right? Also in this case. But the thing is, like, how can we diagnose if your machine learning model is not working very well? Like, of course, you can draw the frontier, but something that it can be easier done is just to compute the confusion matrix. How do you compute it? Well, I think I even have it here. Logistic regression. Okay. Sorry. Okay, so now let's talk the evaluation metrics. First, we need to get to know what are learning curves, confusion matrix, the ROC curve, and the AUC. So let's start. The learning curves usually are, you need to track how does the loss evolve with each step of all the data. You know, the data passes through your model, and then you need to compute like 1 point of the loss, and then the data goes back, then the data goes in again, you compute another one. So the idea is that you minimize the losses we were saying before, and the accuracy needs to go up. So one way that you can diagnose your model is just to plot the learning curves, and you can see if the loss is going down or if the accuracy is going up. If this is not happening, then something is wrong. And also we are plotting for both cases, for the training and for the validation, like for both cases. And okay, this is what I actually wanted to talk about, which is the confusion matrix. So the idea is that you want to plot in a matrix the, let's say, the correct guess and the incorrect guess of the data. So you're going to have a true negative, a false positive, false negative, and true positive. So the true negative and the true positive, meaning true class 1 and true class 0, for example, or true class 0 to class 1, are going to be in the middle. And usually when you have an algorithm that is performing very well, you're going to have a diagonal confusion matrix. So this is what we need to compute here. So from all of our data that we had, I think 1,000, was it 1,000? Yeah, but we split, I think, right? So from all of our data, that it was 1,000, 30% belonged to the test set. And then from those 30%, which were 300, 127 were correctly classified as class 0, which could be, I don't know, blue, right? And 126 were correctly classified as class 1, the other color. And 24 and 23 were misclassified. So those points were probably belonging to these regions where we couldn't draw correctly the frontier, let's say. So the idea is that you need to get this a diagonal. If you don't get this, then something is wrong. Either your data, either your algorithm, something is wrong. There are many things that you can do to improve it, but so far, this is like one of the first checks. Then tell me.
If you have like unbalanced classes, it should be best to plot the confusion matrix normalized, right?
Yeah, it's better to have balanced classes when you train your model in the first place. Sorry, I didn't say that. So you need to check if you have 50%, 50% of the two classes, because otherwise you're going to bias your training, you know? It's not going to be able to learn very well the class that is having less data.
And then I know there are like some techniques like oversampling or undersampling.
Yes.
I know in your experience, what should we do?
When it's unbalanced, what I did in my experience was to try to get rid of some data so that I can have balanced classes. Yeah, because otherwise you can really see the differences. As you say, the biases.
Okay.
Yeah.
Tell me.
how dependent we should expect that these models could be about the random state that we fix at the beginning, that we were.
It shouldn't be dependent. It shouldn't depend on the random state too much. So the idea is that actually, okay, these are just the numbers, but if you want to be very systematic, you can run it many times and you can actually compute the error that introduces this random state, for example. There is also like some, how do you say, intrinsical error that comes with the training also, because you're picking up sometimes the like some amount of data, it passes through the model, you know, and then it depends on which data you're picking first, which data you're picking second. So you need to compute it many times so that you can get the error. So I wrote 126, but the good practice would be to normalize it. So it would be like 0 point, you know. Another question? Okay, so we can continue. And then the next. So, okay, bear in mind this, please. And then the accuracy, which I was telling you before, that is this percentage, you can calculate it actually by computing, like summing up the true positives with the true negatives, and then over all the data. Okay, and now let's talk about the ROC curve, which is the receiver operating characteristic curve. Sorry. It's just that since I'm going here and there, sometimes I forget. Remind me, please, if I do that again. Okay, sorry. Okay, so the receiver operating characteristic curve basically is you obtain it by plotting the true positive rate and the false positive rate. A good classifier, it should, let's say, be very close to 1. So the curve should be something like this, because you want the true positive rate to be like very high, while the false positive rate to be very, very low, right? But let's say a random classifier, which is just out of randomness, let's say you give a test to someone who doesn't know anything about the topic, and this person just does randomly the answers. So this is this dashed red line, basically a random classifier without having any training, or not really, let's say, a person who hasn't studied for the test, for example. Okay, so the idea is that you should have the curve closer to 1, like this, and then you can get a number from this ROC curve. So we call that curve ROC, just ROC. And then you can compute the area under this ROC curve, and it can give you a number. And this number is basically how much of a good classifier is your model. So the closer it is to 1, as I told you before, the better it is. The closer it is to 0, the worse. And now let's do this in our notebook. So here I wrote a little bit of this theory that I just told you, if you want to read. So now we import it. As you can see here from Skylearn, from scikit-learn, sorry, you can actually import the confusion matrix directly. I mean, you can also do the exercise of do it yourself, but if scikit-learn already has it, it's good. And then you can also import the ROC curve and the AUC score. So with those, you can actually plot it, and you can see how much of a bad classifier is our logistic regression model. So you can see that, okay, 0.84, not so bad, but still bad, right? And the random classifier is here. Okay, so that's with respect to the logistic regression. So maybe now we can open the third notebook. So far is understood what we just said? Okay. And then please open the neural networks. Neural networks. Okay. So a neural network basically combines all these ideas, but in a very powerful way. And what is a neural network? Where is it? I think I didn't put it. Okay, it's here. So a neural network basically is an architecture that is based on neurons. It has many layers. Each layer has many neurons, depending on your problem. You're going to have an input layer, as many hidden layers as you need, and an output layer. So the input is going to take your data. The output is just going to give, in our case, a classification, right? Either 0 or 1. You can also do a multi-classification. So it could be 0, 0.2, and so on. You can have a different, let's say, cut over the probability numbers. But in general, like for our case, we're just going to have 0 or 1 because we're just starting. Okay, if we go very close to one of the neurons, this is what is going to happen. We're going to have, x1, x2, x3, as many data xn, let's say, as we need. We're going to have the weights that are going to be basically the, I deleted it? I don't know. The weights that are going to be basically our intercept, our slope, right? As like a comparison. I don't know if you can. Do that like this. And these are going to be our weights. So this is going to be our weights, and θ2, our biases. Okay? So the idea of the neural network is that you want to learn these weights and you want to learn the biases with the data that you are taking. And for that, you need an activation function. So each one of the neurons of the architecture is going to have basically these operations. We need to update the weights, the biases, and the activation, don't forget. In our case, as I told you before, we were working with the sigmoid function, but we can have many activation functions. I will talk about this a little bit later. So, okay, yeah, actually later is now. So we have many activation functions. The one that we just saw, it was sigmoid, which is like part of the logistic regression. But usually the sigmoid is put at the end of the last layer because you want this probability from 0 to 1. There are other activation functions that, let's say, as a good practice, they are introduced in the middle of the, like after each one of the neurons. So for example, one that is very famous is this ReLU, because apparently sigmoid has some problems, let's say, of divergences. To be honest, again, I'm not a mathematician, so I didn't develop like the mathematical tool for it. But I know that the sigmoid usually only goes for the last layer because of these problems that it has. So in this case, ReLU or leaky ReLU are the most used for the neurons that are in between, like for the neurons of the layers that are in between, like these ones. And the sigmoid usually is put at the last because you want the output of the probability, between 0 and 1. Okay. So should I talk about the optimizers now? Yeah, I think so. Okay, so now let's talk a little bit about the optimization that we were discussing before, right? In this case, it's very obvious which is the global minimum. But you can have a problem with your parameter space, and probably you can get trapped in this local minima. So the idea is that you're going to have some optimizer, and this optimizer is going to fine-tune the step in which you're going to explore the parameter space. So, okay. As I told you, the idea is that we're going to compute the weights. But what is happening inside of a neural network? Data. You do a forward pass. In each one of the neurons, you're going to have these two operations, as we saw before. Then you compute the loss, like you're going to pass all your data till the end, and you're going to compare the prediction and the true value. Once you compare them, you're going to have this score, and then you're going to take all this information back to the beginning. So this step of taking it back to the beginning is called backpropagation of errors. And so in this case, we're going to update our weights. So we're going to have information from how far we are from the reality, let's say, from the truth. And then using this information, we're going to update our weights. So the new weight is going to be based on the old, and we're going to compute the gradient of this loss function, which in our case is going to be this one, right? With respect to the weight. And here we have a parameter alpha, which is going to be called the learning rate. So you need to fine tune this learning rate because it basically controls how big the steps are going to be. So for example, if you have this case, say you have a learning rate that is very big. So you go from here to whatever, here, and then from here to, I don't know, there. So you kind of miss this minima, right? So the idea is that you need to go slow, but also not so slow. If you go very slow, then your training is going to take also years. So you also don't want that. You need to optimize it. So the learning rate is the step.
That's like it's too slow, you're gonna get trapped in a local.
You can get trapped in the local minima, yeah. You can go up all the way up to here, and then you are not going to be able to get out of this. So that's the alpha parameter. Also, there are some interesting techniques that actually make this learning rate a variable. So you start with a particular learning rate, and then it starts to decrease, upon the exploration of the parameters. Yeah.
The alpha is a constant during the process.
Like, exactly. Depending on the optimizer that you use, but for example, if there is an optimizer called Adam, and for that one, it is depending on how you are exploring the parameter space. So it kind of auto tunes, something like that. Okay, so once we do the backward propagation, we compute these new weights and the biases. And okay, we repeat. So up to here, sorry, I made a mistake. Up to here, this is called one epoch. Like one pass of all the data, you bring it back, you do the update of the weights, and that's one epoch. So the idea is that you need to repeat this process many, many times until you get like good values for the weights and the biases, so that your final prediction is going to be very close to the actual truth, if that makes sense. Yes? Somebody has a question?
Yeah. In order to update the parameter, I mean, at some point you have to, I mean, you always update the parameter, that's the question? Or is there some epoch that you can go further down and you, like this car, this epoch, and you keep or you're always updating, and at the end of the process, you choose which combination of the parameters was the best for the.
Yeah, like what you do is that, this is a good question actually. So when you have the weights, so each one of these connections has one weight and one biases, right? One bias. This one, this one, this one. So as you see, there are many connections from this neuron to this neuron to this neuron. So you have many weights, many biases. Also this one is connected to all of them. Many weights, many biases. All these weights and biases, they are initialized randomly. So you actually don't know at the beginning because they are completely random. But the magic is that since they are random at the beginning, you are trying to minimize, right, the loss function. So you are updating the parameters in such a way that you are finding this minimum. So in principle, of course, there is a point in which you're not going to update the parameters anymore because they are already, sorry. So the idea is that you are going to minimize these two parameters until a point in which maybe, I don't know, you're going to be very close to the value. So it doesn't make any sense to keep training. So there is a method called early stopping. I mean, I didn't talk about it in the whole course, but just as a curiosity, there is a method called early stopping, and it's really, yeah, it's called like this. Just in case. Early stopping, if you want to check it. So what this method does is that it tracks basically the accuracy. And if it doesn't go up anymore, then it stops. It tells you, okay, your model is already trained. Am I over time?
No.
Okay. It tells you that your model is basically already trained and you don't need to train it further. So this method is really cool. But okay, tell me.
My question is, as the initial values of the viruses and the weights are random, we don't really know the exact shape of our loss function. So how can how can we be sure that we are reaching a global minimum and not a local minimum? Because, for example, when we use early stopping, I think that it stops. Okay, it doesn't goes up anymore, but that can be a
local minimum.
not a global one. So
Yeah.
is there a method in which we can be sure that we are reaching a global one?
So what is interesting is that this early stopping method has one parameter that is called the patience. Wait. And you can fine tune it. Say that you want to train your model for 1,000 epochs and you want this patient to be, I don't know, 50. If you have 1,000 epochs and you have 50 as a minimum for tracking, then you can be sure, you know. But if your patience is, for example, 3, right? Then you could be trapped in some local minimum. So I think that the patience is important so that it's not like, okay, I arrived to 1, okay, bye. You know, it's okay, I arrived to 1, but I'm gonna be in 1 until 50 more epochs. And if I am still in 1 in 50 more epochs, then okay, I'm gonna stop. So the patience is really good for that. This is just a curiosity. Yeah, you are very clever. I didn't prepare this part. Good. Okay, so I think I discussed this. We can start training a neural network. Go to the learning curves. Yeah, I think I covered everything. Yeah, okay. Maybe we can talk about this later. Let's go to the third. Oh, sorry. Yeah, to the third, which is 0, 2. And there, okay, I wrote a little bit of the theory, so you can read whenever you want. And again, the magic of scikit-learn, we can we can import, sorry, we can import the linear regression, the logistic regression. I think I just copied from the previous part. This, so we just run this part, the imports. And now we're going to simulate exactly the same data. So we're going to work exactly with the same data, and we're going to see how a neural network is able to draw this frontier like more accurate in comparison to the logistic regression, which is just kind of one neuron, let's say. So we have the data. Again, we have the 2 classes, the 2 parameters. We have the same. We split the data, 30 and 70. And okay, and we arrive to this point. So for this, I'm using TensorFlow. You can use PyTorch too, but I like TensorFlow just because I started to work with TensorFlow. You can use both. So in TensorFlow, from TensorFlow, you can import this called sequential that is going to be able to, like, you can import, you can explicitly say how many layers you want and how many neurons you want in each one of the layers. So sequential, and then dense is going to be a layer that is going to be, where is it? Okay, so whenever you see dense, it means that is fully connected. Because sometimes you can have that this neuron is connected to this one, but maybe it's not connected to that one, right? So when you see dense, it means that it's fully connected. So we go back, and here we define our model. So we have 3 layers. The first layer has 20 neurons. We have an activation function of hyperbolic tangent. The second one has 20 again, and the third is going to have 1 because we just want the classification, right? And again, the activation is going to be the sigmoid because we are computing the probability. So we compile, and in this case, we are writing that the optimizer is going to be Adam. So it has like already the, let's say, an internal learning rate, but you can specify later it like explicitly. I'm not specifying it, but you can just say optimizer Adam. The loss function, because we are working with a classification problem, is going to be a binary cross entropy. So usually the loss function that you use depends on the problem that you're trying to solve. If you are trying to do like a regression, for example, if you want to have like your last output to be a number that is continuous, not just 0 or 1, or not a probability between 0 or 1, but an I don't know, age or something like that, then you're going to use another loss function. But in our case, right now, because of this classification problem, we're using binary cross entropy, okay? And the metrics is just, what do I want my model to look at? Like the accuracy, the loss, what do we want? So in this case, I just wrote accuracy. You can also write loss. You can also write the validation accuracy or the validation loss. In my case, I just wrote the accuracy. So let's see what happens. And finally, when you have already compiled the model, you feed it with the training data, with your labels, and then you specify which one is your validation data. So the parameters and the labels again, and then I'm specifying the epochs. So in this case, I'm just training for 100 epochs. You can train for like 1,000, as I was saying before. So, but this is just to see how it goes with 100. So, are you running it locally? Well, not locally, but in the collab. Okay. And you can see, check this. The accuracy, it starts in 0.76, right? But as we are going to pass all of our data and then do it again and again and again, the accuracy is going to increase, right? And then we finish with a value of like 0.94, which is quite good. And then check out the loss. Yeah, so it starts in 0.6. And then as we are training again, it starts to go down, right? So it is doing what it is supposed to do, fortunately, because it's not always the case. Okay, so now let's see. Oh, sorry. Once we have trained our model, what we need to do is to compute the probabilities of the data that it hasn't seen before, right? So we're going to compute for the validation, the predict, and also for the training. In principle, as I told you, this is just pedagogical, but I should have like a test set, a separate test set that it hasn't ever seen before so that we can actually see, oh, is it actually performing good or not? In this case, we're just using the same data set because I just had 1,000 realizations, so it would be too little maybe to make like a full training. So I'm using the same training and validation. And in this case, I'm saying, look, that our threshold for classifying is going to be 0.5. We're having the sigmoid function, right? And in 0.5, above, we're going to have one class and below another one. And okay, and then we're just computing the accuracy. Let's print these 2 values to see. I mean, we already saw it in the training process, right? But we finished with like 0.94 and 0.91, so it's quite good. And now let's plot the decision for boundary. You see? Before we had just a line, right? So there were so many points that were misclassified. But in this case, because we have so many neurons, okay, not so many layers, but at least many neurons, we are able to draw this boundary more correctly, at least. Of course, we still have some data that are misclassified, like here and here, but also they are a bit mixed with the data from the other class. So maybe it would be very difficult, to have these ones. Like usually in the boundaries where you have more problems.
Yeah.
Tell me.
We pass to the solid or the classification labels after the training. How is that inside the training? There is returning some value like accuracy if it's not if it's not still the labels.
Sorry? Again. I
Sorry.
dissociated. Sorry.
The part of the part in which we translate from probabilities to the solid labels to
Yes.
is after we train, but during the training it is calculating some kind of accuracy. I suppose it's calculating difference.
You mean how is it calculating the accuracy given that you still didn't assign a solid label, but just a probability, right? I guess that it's also 0.5, I guess.
Okay, it could be the default.
Yeah. But there is also another method that can play a little bit with this 0.5, because as you can see, there are problems in the boundary. So sometimes you can have that exactly, if you have a probability that is exactly 0.5, could be either one class or the other, right? So you need to kind of randomize this a little bit. And there is also a method for that, but I have never used it. I mean, I learned about it, but I have never used it. Yeah, that. And finally, yeah, done.
On the previous problem with logistic regression, we're using mean squared error, and
Yes.
now we're with
Binary cross entropy.
Okay, and this one, does it have like is it similar in the sense that it penalizes you how far away you are from the map?
Yes, exactly.
It's similar to that?
It is similar in that sense.
But it's more general because I can imagine that if you have like a higher dimensional problem, a surface is not going to help you.
It is general.
Okay.
Yeah, because it is assuming like you have vectors instead of just an X or a Y. So it is more general, yes.
And the name comes from because it looks like an entropy. And you're crossing things.
I don't know. I don't know where it comes the name.
Why not?
Yeah.
Like
It's some, yeah. Yeah, but yeah, good point. I never even thought about why it's called binary cross entropy, but thanks. Okay. So, and now let's compute the confusion matrix. Well, I already have it there, but you can run it locally. And you see that it performs better if we compare it to the previous one, right? Here is 138, 100, okay, not much better, but okay, 127, 126. And this one is 138 and 136. So, okay, it is improving, right? Okay, and finally, let's draw the rock curve, and it's 0.91. So the previous one was, I think it was 0.88 or so. So we are getting there, right? It's improving a little bit. But where you can see it, actually, it's here in the decision boundary. Here it's very obvious that it's learning more interesting patterns than just a straight line. Okay. And then finally, let's compute the learning curves that were the ones that I told you before. So here we're going to track. Each epoch is going to, we're going to compute the loss and the accuracy. I think I already showed you in the training process. Where is it? Here, right? We were checking the accuracy and the loss, and the validation accuracy and the validation loss. So the idea is that we want to plot all these per epoch to see how it is evolving. Please, if you get lost at some point, let me know. Okay. So you can see that maybe here we were kind of trapped, right? in a local minimum. You can see a bit obviously, right? Because we were not able to go out from here. But maybe in the epoch 80, it started to go down. So maybe something happened, maybe the learning rate, something happened that we were able to get out of here. And also you can see the same reflected in the accuracy, like it starts to go up and then we get trapped in some minimum and then we get out of it. So we kind of reach 1, let's say. So this is more or less how you understand if you are trapped or not in a local minimum. And okay, and that's it for the neural network part. So let's go to this part, normalization. I mean, I didn't explicitly write an example of normalization, but you are going to have to use it in the afternoon session. It's very simple. You just have to import it from the scikit-learn. So the idea is that when you have data that are not normalized, it's difficult to compare, right? The idea is that you need to normalize it so that you will be able to have the same scales. So how do you do this? You just compute, let's say, you have a new parameter that is going to enter to your neural network. And this is computed by like finding the minimum, the maximum, and so on. So you can just regularize it. So it happened many times to me, and probably you will also see it in your scientific career, that you can try everything. Redoing the data, finding 360 machine learning approaches, modifying the neurons, adding a layer, adding the activation functions, I don't know, doing 300 things. And in the end, the problem was just the normalization. So this is super important. And it's actually not a part of the neural network itself. It's something that you do before training. So before you need to do the normalization, if it is, I don't know, if something is wrong with your neural network, you have to try to do it before, then you retrain, and then you will see like the impact of it. So in the afternoon session, we're gonna do this. And okay, now let's talk about what you like, cosmology. So I prepared an example on the cosmic microwave background. How many of you have worked with the cosmic microwave background? Can you raise your hand? 1, 2, 3, 4, 5, 6, so many. Good. Okay, but how many of you, all of you know what is the cosmic, all of you are cosmologists, good. I mean, it happened to me that I was teaching a course in the physics department, so people were like, no, we actually, I heard about it, but you know, okay, so the idea, as you know, we have these tiny fluctuations that are on the temperature that are of the order of 10 to the -5. So we can, they are scattered across many directions in the sky, so we can compute these spherical harmonics, and then we can have the angular power spectrum, right, from the coefficients, the variance. We can plot it. This is the data belonging to Planck, the legacy before the new results of ACT. But the idea is like, how can we use this neural network classifier with this data if I already kind of know, okay, we kind of accepted at least until last year that the lambda CDM model was widely recognized, but okay. So of course we have the lambda CDM model. We know that almost 70% of it is of the content of the universe is dark energy. Almost 27 is dark matter, and only about 5% we have as ordinary matter. But then we have alternatives, right? Because we cannot detect what is dark energy. We don't know still yet what is dark matter. And there are also many problems, as you may know. I don't want to talk about it. Maybe you already talked about it 300 times. So we have many alternatives, right? Could be modified gravity. We could talk about some maybe non-trivial early universe physics that happened, or maybe, of course, the star of the year is dynamical dark energy. We still don't know. But the idea is that there are some subtle features in your data that you can get some insights from. This is a plot from a paper actually, and say that you have a non-standard feature in your angular power spectra. This is of course not the data, just the theoretical prediction. Of course, if we just look at both outputs, the lambda CDM model and this non-standard feature, which is an alternative model, they just overlap, right? We cannot see any difference. If we compute the differences. But the idea is that maybe you can use this to kind of understand something about your theory. Like you use your data to understand something about your theory. How? You use your theory to simulate your data, to train a model, and then you use it in the real data. Does that make sense? Yes. Good. Okay, so your turn is later. So we open the CMB example notebook. Okay. So the idea is going to be the following. We're going to have this CMB-like power spectra. I'm not going to use class. I'm not going to use anything. I'm just going to use a very simple simulating strategy. And we're going to have class 0, which is going to be like lambda CDM-like. And the alternative model is going to be class 1. Whatever. I use just this localized oscillatory feature, like the slide that I was showing you before. So let's import our packages. Again, okay. Yeah, let's import our packages. Let's run. By the way, is somebody having any problems running the notebooks? No? Wow. To work with the 2000Ls, which are like the multiple moments. And then I'm just going to, this is just for simulating the data. So I'm really not using any physics motivated like a class or camp, Boltzmann solver. So you can just run it. You don't need to go through it. So more or less, this is very widely approximated, but more or less, this is going to be our shape, okay? And we are going to add some noise. We're going to bin the data and add some noise. So our data is going to be a little bit like this, and this is going to be the uncertainty. I just wrote, I think, 0.02 or something like that, like the fraction of the noise. So the bigger we have the data, the bigger is going to be the error as well, right? And the smaller we have the CL, then the smaller is going to be the error. So this is why you see this error bus. And okay, this is just to plot. If you see the next, this cell, again, is just to perform more realizations, and you can see, wait, what happened? Okay, here you can see class 0, lambda CDM class 1, this feature. We run it. And then we want to plot to see more or less how our bin data looks like. So we're going to have two cases, right? The lambda CDM, which is going to be this blue, and this feature model, which is going to be the orange. I just took two examples, but remember that these also have the uncertainty, like, okay? The next is for doing 3000 realizations, I think, and for reshaping. And now we do the machine learning part. We have to split in train and validation sets. In this case, I wrote 0.25, but I mean, before I was writing 0.30. We can do that if you want for being more systematic. We run this. Okay. And then, okay, one thing that I didn't tell you before, but this is also important, like to clear your session whatever thing that could be stored, or if you're running like the same code multiple times, if you are training and if you like change something and retrain again, then the weights are not going to be reinitialized. They are going to be stored with the last session. So it's good that you do this every time that you want to retrain. So don't forget about that. Okay. And now we are going to define our classifier. We're going to have 2 layers, just simple. Let's keep it simple. One, which is going to be a dense of 64 neurons. And the last one, which is just going to tell us the class, if it's belonging to the simulated Lambda CDM, or if it is belonging to our alternative model, right? Like this oscillatory model. So that's the idea. Is the idea clear? Yes? Okay. Completely sure? Okay, so we do that. This option is also very nice. Okay, you compile it, you write here, look, I wrote Adam. I wrote it like this. Before we just said optimizer Adam. And here I wrote like TensorFlow, Keras optimizers Adam, and I can specify what is the learning rate that I want. Here I wrote 10 to the minus 3. Like it gets updated anyways. The loss, we're going to use again binary cross entropy because we're having a classification task. We're going to have the metrics. And then, yeah, we just make the model. This function is also really cool, model summary, because it tells you which is like your architecture like. You have the layers, how many, what is the shape. Here it means that you have 64 neurons in one and one in the last one. And these are the parameters of each, meaning you have the weights and you have the biases of each one of the connections, right? Also, one more thing. I wrote dense, which means fully connected. Perfect. Thank you. Okay, so let's train. Are you training with me? Yes, good. Okay, so again, I wrote 100 epochs, but you can train it for more if you want, just to see what happens, just to see if this decreases or increases. You can do it for more if you want to check. Just you need to modify it. Where is it? Epochs, right? You need to modify the epochs, and then you're going to have more or less epochs. And this is also interesting that I didn't say it before, a batch size. Does somebody know what is the batch size? No? So if you have, let's say, 1,000 simulations, if you pass like on one, let's say the 1,000 simulations, you can have some problems. So it's good to like slice it down. And this is, I wrote 32 because usually in like 16, 32, 64, you know, because this is like the information usually that is like managed in computer science, right? So this is why I wrote 32, but you can also write 64 to see what happens. Like you can play a bit, you know, with the architecture if you want. And also this option, verbose, it's explicitly saying 1, which means that I want to see the training process. I want to see how is the accuracy updating, how is the loss updating, all this. If you write 0, then it's just not going to output anything. It's just going to tell you, oh, the training has finished. But I like to see, you know.
Yeah, the difference is not the training, but what is the,
Like right now, I just wrote the number of epochs.
but in general?
In general, you can use this early stopping. I didn't prepare it because I thought it was just going to be very basic, but in general, you can use this early stopping, which is also included in TensorFlow. So you just say import early stopping, import callback early stopping, something like that I can show you later. And then in early stopping, you can give a patience. That the patience is like the amount of epochs in which we're going to have a constant or close to constant accuracy or loss. So if the accuracy is very high and you have it, so this is wrong. I was telling them that 3 is too low. But if you have, for example, 50, okay, in this case we have 100 epochs. Maybe the patients, let's put it in 20, for example. So if you have the patient that is going to be 20, it means that for 20 epochs, the accuracy is going to be very high, so you can stop the training, not to overtrain, let's say. So that's the criterion in general, but in this case, I just wrote 100 epochs. Yeah.
Possible that you leave the local minimum and enter the global minimum and enter a local minimum and it stays there.
You mean that once you have arrived to the global minimum,
Yes.
it jumps to another local minimum?
Yes.
It's not, because you have already like minimized this loss function. Like you are already trapped here, let's say.
Okay.
Yeah.
So
You're already trapped, you cannot escape.
because I was looking at those numbers and sometimes went lower, sometimes went up.
Yeah. If it is a slight, the change, then it's okay.
Okay.
Yeah. Sometimes it goes a bit up because you are doing this like you are jumping here a little bit, like moving here a little bit, but you cannot go too far.
Okay.
So that's why.
I have another question. You train this 100 epochs, and then the last model, the weights that you have, the train model, will be the weights at the last epoch, or it will choose the one with the lowest loss?
It will be the ones at the last epoch, but those are in principle going to be the ones of the lower loss if your model is trained well, in principle. I mean, plus some little fluctuation, but if it's trained well, then it should be the same. If that makes sense. Does somebody else have a question?
At some point, you show something that you can choose, like what the neural network is going to look at to do the validation.
Yeah.
For example, you showed that you're doing accuracy.
Yes, I think it's here. I know this is just the print.
No, but at some,
Yeah, when compiling, right?
is it possible to pass multiple things?
Yes. Yes.
Yeah, they're
Yes.
Yeah.
Yes, I think you can. I don't remember exactly if it was like this or you had to put it all in one. Let's try. Yeah, it's working. So here, and we can retrain. Oh, sorry, I need to. Okay, then no. Then no. I don't remember if it was like you need to create one whole like list or you need to, but you can pass many at the same time. Okay, let's compile it and let's clear the session. Yeah, don't forget to clear the session. I'm saying it because it happened to me. I was like, it's actually training. And then somebody else downloaded my code and they were like, what are you saying? It's not training. And I was like, no, it is. And it was because I didn't clear the session and yeah, whatever. Okay, so, and now, okay, now the idea is that our model is trained to tell us whether the data that, any data that we give it from the angular power spectrum of the cosmic microwave background belongs to some particular theoretical model. Is that okay? Clear? So if it is trained well, yeah, okay, more or less. The loss is more or less okay, right? It's going down kind of steady, but the accuracy is a mess. Especially the validation accuracy is a bit of a mess, but it kind of goes up, which is the most important thing, that it needs to go up. If you see a model that is not learning anything, it should be just like around 0.5 and just fluctuating like this, and also the loss.
Yeah,
Yeah.
if you have something like the float at the top, would you recommend to increase the number of epochs to see if it's
Yes,
If it's still
if it's
decreasing or-
still going down. Yeah, because here it doesn't seem to be going to zero, right?
Yeah.
Like we can even check here, what is the loss? The loss is 0.25. So actually we can, if you want, we can make the experiment to increase the number of epochs, whatever, 200, right? So let's see. You see the loss?
Decrease.
0.19, and it was 0.22, right? 20 something, right? So, I mean, we can also fall in the trap of saying, oh, the more I train, the better it gets. But there is a point in which it doesn't make sense to overtrain. You can overfit. So the idea is to have this balance, like you need a very well-trained model, but at the same time, you don't want to, one, spend a lot of computational time, and two, to overfit. So, okay, and now we can see what happens to the plots. Now that we changed, okay, much better. Now it looks nicer. This was a mess. Now it looks a bit nicer because it looks like it's kind of converging, right, to one slowly. And the same here, converging to zero. Okay, and now let's compute the confusion matrix. And yeah, it seems quite good, right? It's quite diagonal. So again, this means that 379 simulated data of the angular power spectra who belong to, for example, lambda CDM, classified as lambda CDM. And in this case, it means that 434 of our alternative model, that is also the same data of the angular power spectra, were correctly classified also as the alternative model. So only 16 and 71, well, 71 is a bit, but only these two numbers seem to be misclassified. Which kind of makes sense because you are introducing also scattering on your data, right? You're having noise. So we are not having like perfect observations, right? We have a lot of noise in our daily lives, like in physics, everything. Like when you take data, you're always going to find these uncertainties, errors, noise from the instrument, atmospheric background, whatever. You always find these things. So it's important also to understand that. And okay, let's compute the rock curve. Oh, tell me.
So then the error bars are too big and we got a model that's way too perfect. Does that mean it's overfit or?
What is interesting too is that if you are incorporating the same noise to all your data, let me think. This is something that we were doing in our research paper. If you are incorporating exactly the same noise to all of your realizations, so for example, yeah, maybe I can. This one was a very useful plot actually. So say you have these two, let's say, yeah, you have these two models, right? Like this one, sorry for my drawing. And two, which is a little bit lower, I don't know, maybe even overlapping. Yeah, whatever. And then you have the binning, you do the binning. So you're gonna have the points somewhere over there, but at the same time you introduce the noise. So your actual points are going to be scattered, right? Like this, something like that. I'm exaggerating, but they are going to be scattered. If you are introducing this scatter, this uncertainty, also to the other model, it should be the same distance. So in principle, your neural network shouldn't be trusting much on this information, but instead learning the underlying theory itself, if it makes sense. Okay, does somebody else have another question?
For example, on the data that you showed us on the notebook, mean, it was more or less visible that on the differences are on the largest scales.
Yes,
So can it make sense to, for example, to keep the data up to L500?
yes,
And that should improve your training, right?
yes, yes,
Yeah.
yes. It would completely make sense that you get rid of this. Like, I mean, here, but sorry, go ahead.
Yeah.
Tell me.
But the following question was, it is more likely to have more noise on larger scales. So
Yes,
that's kind of a drawback of doing this. And
this is also a good point. This is also a good point because you have more noise in this part on larger scales. In the real case, I think, like, at least for me, I use the full 2,500 kilohertz because here you can also see some differences in these parts.
yeah,
So maybe the model can rely also, I mean, you would have to make the, how do you say? You would have to make the analysis to see exactly what is relying on, and this is what we are going to see tomorrow because we're going to talk about interpretability. We're going to try to understand which regions of this data are going to be more important for a neural network. And it's actually cool because, okay, now we more or less know how a neural network works. We are not mathematicians, we are not developing the theory, right? But we more or less know that we have these linear combinations, these activation functions, and so on. But it's difficult to get this connection of the output to the direct input. Because, come on, we have so many, like hundreds of connections, hundreds of weights, hundreds of biases, so you cannot keep track of all of them, right? So you need to have a method to kind of give you like, okay, maybe this, for this particular class, I'm looking mostly at this part, or at this part, or that part. In this case, you are right. I think the most important part should be here. If your neural network is learning what is important, right?
so if you use the full up to the smallest scales, then can that penalize the training or it doesn't hurt that much?
I think it doesn't hurt much.
Okay.
I don't think it penalizes the model because in the end, it's just I'm using this, where is it? Of our notebook. Okay, I think this is just a waste of computational power, if you ask me. Because it's from 500 to 2000, right? Here is not much, it's like what? Okay, like 500. Okay, no, 1000. Yeah, maybe it's also a bit of a computational waste. I made a computational waste, I'm sorry.
It's just efficiency, no?
Yeah.
It's not going to affect your
No,
training
it doesn't
and
affect your
response.
training. It's just efficiency, yeah. Tell me.
Barbara, in this training we're doing right now, we are including the uncertainties.
Yes, we are including the uncertainties.
We are taking just included or implicit in the data, or we are giving the network the information that.
No, we are not giving the network the information. You can also do that actually, like, for example, data point, uncertainty, data point, uncertainty. But in this case, we're just giving the data points without the uncertainty because it was connected to what she asked, Charlie, right? I'm sorry, I didn't ask your names. Maybe in the copyright so that I can know. So the point is that you're going to have these uncertainties, right? But if in the end, the uncertainty is going to be the same for the two models, then the network shouldn't be looking at the error bars. The network should be looking just at the underlying theory, because it's going to be the same distance apart. See, if that makes sense.
Another question, maybe this question is not so useful for this case of classification, but for a regression, could network, neural network return the uncertainty, differentiate uncertainty along regions, or we are fixed or stuck in a situation where we can just obtain uncertainty, constant uncertainty for all the regions we are training?
Like, it is not constant. It is constant for the two models, but each one of the data points has a different uncertainty. Like, I don't know if I understood your question. I'm sorry because I dissociate sometimes. Um, what I wanted to say is that like you have the error bars, right? And then it's not the same error bar for all the data points. This is what I wanted to say, that it varies, but it is the same for the two models.
Yeah, okay, I understand that, but I was talking more about if we were dealing with a regression in using neural networks,
Yes.
and we want a curve defined,
Yeah, you want just some.
then using neural networks, we can obtain a curve with a variable uncertainty. It is possible to obtain that with a neural network.
So that you can, instead of having a class, you want to know the uncertainty, for example.
Yeah, but I suppose it's different for regression than scale.
Yeah, it is different.
Become like a confidence region, yeah, this.
It should be possible depending on what you want in the end. So, because in the end, you're computing. In the second case of the regression, yeah, you're computing like a variable that can get any, it can get any number, let's say, upon your problem. Yeah, I mean, I have not done the exercise myself, but I can think about it. Thanks.
I think that there are methods. I mean, when you work with regression, with neural networks, you can have like a simple output. It would be like the mean value, but then you can have a network with multiple outputs.
Yeah,
And
exactly,
then
that's
you can
true.
have like sort
Two
of like
different.
a probability density function.
Yes.
So it contains like all probable values that you can have for those parameters.
Yeah.
So in that case, you can plot like the uncertainty and the mean
And the mean
value
value.
that would output a single output of the mean.
Yeah,
And
makes sense.
there are also models like probabilistic models based on neural networks that do that. Like the output is a probability density and then you use it as a
That's very nice. Yeah.
That the goal in that case is you can design your own neural network and a specific neural network to receive that its outputs like uncertainties, the mean values, probabilities. It depends on it.
On what you want to. But in general, I mean, you can also get many things at the same time. It depends. Like now, I just showed you the output layer that only has like one neuron, but you can in principle have many output layers and you can get many things at the same time. Like now we can just get the class, but for example, what if I told, I don't know, the neural network to give me, some other characteristic, an amplitude, for example, the amplitude of this oscillatory feature, for example. Should be possible depending on how you build it. But yeah, this is a really good point. Yeah, and okay, we trained, we saw this, we saw that, and now finally let's compute the rock curve. And here you see that we have a score of 0.9 and it's kind of okay. So it's kind of working. We can be proud. Okay, so we have 14 minutes left, and I was thinking we can discuss questions if you have more questions.
Yeah.
And then in the afternoon, we do the hands-on. I finished a bit earlier, sorry. So is there any other question, like, for example, related to, yeah, I don't know, the rock, the confusion matrix, is it clear?
I wanted to ask something because on this, for example, when you have two models, the example you gave on the notebook of the CMP power spectrum, you are like only deciding of if your model is preferring one model or the
or
other.
the other, yes.
You can do extra stuff, like for example, if your model has extra parameters, you can output like at the posterior on the parameter.
Exactly, exactly.
But that problem is quite different, right? You're going to basically change a lot of the
Architecture,
and
yes. Yeah, you can output the posterior too. Like in the end, neural networks can approximate any function, right? That's the magic of it. So you can, yeah, you can output the posterior distributions. You can do many things with it. It could be changing a little bit. There are also Bayesian neural networks, and there are like, yeah, tons of things that you can find online.
I have a question. Is there a way to know how many neurons do you need for the size of your sample? Because I imagine like in the parameter space, you have way too low number of points. And you have way too many neurons. You can maybe overfit there. Is there a way to know how much?
It is a really good point. Okay, two things. The first one is that usually you would like to go from a bigger amount of neurons to a lower amount of neurons. So that's the first rule. Like if you start with, I don't know, you have 60, 70 neurons in the first layer, you could add another layer, but it should go lower, and then another layer, and you should go. So that's one thing. And another thing is that there is this package called Optuna. Has somebody heard about it? 2, 3 people. 4. Okay, good. So Optuna is really good because it has, you can specify the hyperparameter that you want to fine tune. For example, you can choose, you can, yeah, fine tune the number of layers. You can fine tune the number of neurons in the layers. You can fine tune the learning rate. You can fine tune many hyperparameters. And what Optuna does is that it takes your architecture, okay, your one architecture of the that has some of the hyperparameters that you said. For example, I want to fine tune the number of layers. I want to fine tune the number of neurons. Okay, I'm gonna take an architecture that has 3 layers with 20, 10, and 5 neurons each, and then it trains, and then it outputs 1 accuracy score and 1 loss, and then it does another trial with a different number of layers, a different number of neurons, and it outputs again an accuracy and a score. And then it does the same and the same and the same, like it trains. So it is a bit of a long process because you have to train 200 epochs every time that you want to make a test, you want to make a trial for a new architecture. But in the end, you can see the outputs, you can see the accuracy, the loss, and you can get maybe an insight of which is the most recommendable architecture that you can use. So this one is a good practice for your research. Write it down.
The classical method is to run MCMC on the hyperparameters.
If you are not talking about machine learning, yeah. Like if you're not talking about machine learning, the classical method would be you run an MCMC, you kind of explore the parameter space, and then you know.
Yeah, but for the hyperparameters, you could run something.
Ah, sorry, I didn't understand. I don't know. Wow.
But that,
I mean,
conditionally expensive.
yeah, probably could be very I also have never seen a plot of like number of neurons versus number of layers or something. Like I didn't think about it, but
Yeah.
I mean, could be. It's actually an interesting question. Okay, someone else has another
I
question.
can say that some optimizers, like trigonometry, like that, use different methods. For example, CMC or unique method to.
I didn't know that.
Because I recall hearing someone telling me that Optuna was some type of MCMC, but optimized, so you don't have to. I think it's probably you have like access to derivatives, so you are more efficient or something.
Yeah, to be honest, I'm not sure because I remember that when I ran it and I was kind of trying to monitor, sometimes they were completely random, like jumping from 5 layers to jumping to 1 layer and then jumping to more layers. So I don't know, but probably, I mean, it would make sense, right? That it's not random and that it goes like to some system, it converges to some minima, yes, some optimum, yeah. Yeah.
Maybe you can maybe write a neural network to optimize your.
That's a cool point. You can do whatever you want with neural networks. Like they are amazing. Yeah. Okay.
Any more questions? Comments?